Hi, I'm Alex Zabelski.
I'm Megan Farrell.
And I'm Brendan Bench, and today we're going to talk to you about the applications of polymers in fuel cells. Fuel cells have been one of the most intriguing new types of energy production in the past several years and have been heavily researched as a result. Almost all fuel cells work in a very similar manner, with the main differences being the materials used for the anode, the cathode, and the electrolyte. To power the cell, a source of gas, usually hydrogen, is connected to the inlet, allowing the molecules to flow into the fuel cell. The molecules first interact with the anode, which separates the molecule into positively charged compounds and electrons. The electrons are forced to pass through the load attached to the cell, while the positively charged compounds flow through the electrolyte. On the opposite side of the cell, a gas, usually oxygen, enters the fuel cell. When the electrons reach the cathode, they meet up with the separated positive compounds and the other gas molecules. At this point, the original molecule compounds and gas all combine, forming a liquid waste product. One of the more recent innovations in fuel cell technology is the use of polymers in fuel cells. The use of polymers provides a substitute for liquid electrolytes, allowing for the cell to be more solidified and dense. In 1975, a polymer chemist named Peter V. Wright identified that by mixing the appropriate ions into polymers while solidifying, it was possible to bring out properties of ionic conduction in the polymer in a polymer salt complex. His first experimentation was with polyethylene oxide, which is able to hold sodium and potassium ions within the polymer and act as a conductor. Another polymer chemist, Michel Armand, decided to explore the possibility of mixing lithium into polyethylene oxide, which proved to be a rather successful conductor as well. Polypropylene oxide has also been proven to be a viable polymer option. This initial research of polymer electrolytes has led to the research of other types of polymer membranes as well. Beyond salt and polymer electrolytes, other types of electrolytes include plasticized polymer salt complexes, polymer gel electrolytes, rubbery electrolytes or polymer and salt complexes, or composite polymer electrolytes. Despite several types of polymer electrolytes having been established, research on how the solid polymer electrolytes actually work is still ongoing. There are significant benefits to using solid polymer electrolytes in the fuel cell. One of the most significant benefits, as stated before, is the ability to increase the density of the cell. In addition, maintenance of the fuel cell is significantly easier since all parts of the cell are solid with no moving parts in comparison to fuel cells that use a liquid electrolyte. There are also large advantages to using solid polymer electrolytes from a safety standpoint. Oftentimes, the most powerful cells and batteries operate off of lithium ions, as seen in lithium-ion batteries in many electronics today. Lithium-ion batteries have safety risks involved, mostly with flammability and pressure in the packing systems. The use of polymer electrolytes is a much safer way to utilize lithium-ion in fuel cells with less risk, especially since there is no risk for corrosion at the anode and cathode, and no risk for the electrolyte leaking from the battery. The polymer electrolyte also provides advantages in the weight of the cell and the flexibility or shape of the cell. We will now turn to Megan to discuss different types of fuel cells.
Direct methanol fuel cells are powered by pure methanol, usually mixed with water and directly fed to the fuel cell anode. Since methanol has a higher energy density than hydrogen, though less dense than gasoline and diesel fuel, it creates less of a problem with fuel storage for this type of cell. Direct methanol fuel cells are often used in portable applications such as cell phones or laptops. Alkaline fuel cells were one of the first technologies developed and were primarily used in the U.S. space program to produce electrical energy and water on board the spacecraft. Alkaline fuel cells use a solution of potassium hydroxide and water as an electrolyte and a variety of non-precious metals as catalysts at the anode and cathode. Challenges for the alkaline fuel cell include contact with carbon dioxide, which inhibits the performance and durability of the cell, membrane conductivity, higher temperature operation, water management, power density, and anode electrocatalysts. In phosphoric acid fuel cells, liquid phosphoric acid is used as an electrolyte, which is contained in a Teflon-bonded silicon carbide matrix and porous carbon electrodes containing a platinum catalyst. They are typically used for stationary power generation, but are also sometimes used for public buses. Phosphoric acid fuel cells are more tolerant of impurities in fossil fuels than other fuel cells that are easily poisoned by carbon dioxide. When used for cogeneration of electricity, phosphoric acid fuel cells have an 80% efficiency, but when used to generate electricity alone, they have an efficiency of about 40%. Phosphoric acid fuel cells are less powerful than other fuel cells, so they typically have to be larger, heavier, and end up being more expensive. Molten carbonate fuel cells are currently being developed for natural gas and coal-based power plants and are used for electrical utility, industrial, and military applications. These fuel cells run at a very high temperature, around 650 degrees Celsius, and the electrolyte is composed of a molten carbonate salt mixture suspended in porous, chemically inert ceramic lithium aluminum oxide matrix. When coupled with a turbine, molten carbonate fuel cells can reach an efficiency of about 65%, but when used with cogeneration, the efficiency can be up to 85%. Unlike phosphoric acid fuel cells, molten carbonate fuel cells do not require an external conformer to convert fuel cells since they operate at such high temperatures. Methanes and light hydrocarbons will be converted into fuel cells by themselves through a process called internal reforming, which also reduces the cost. The main disadvantage of molten carbonate fuel cells is the durability, because the high temperatures and corrosive electrolytes will decrease the cell life. Solid oxide fuel cells are made of a hard, non-porous ceramic compound and also operate at high temperatures, around 1000 degrees Celsius, which removes the need for a precious metal catalyst. The high temperatures also allow for internal reforming to occur, which reduces the cost and Reversible fuel cells produce electricity from hydrogen and oxygen and generate water and heat as byproducts, just like other fuel cells. The difference is that reversible fuel cells can also use electricity from renewable resources such as solar and wind energy to split water into oxygen and hydrogen fuel through electrolysis. Reversible fuel cells can also store excess energy in the form of hydrogen, which could be key in the future of renewable energy technologies. Next, Alex will discuss polymer electrolyte fuel cells.
The main focus of our research will be on the polymer electrolyte fuel cell, or the proton exchange membrane fuel cell, PEM for short. Hydrogen is the fuel that is used for these fuel cells. Hydrogen provides enough energy to power things such as automobiles and does not produce the harmful emissions that things such as gasoline do. The hydrogen gas that is fed into the anode must be pure hydrogen. Failure to pump pure hydrogen into the anode will cause the impurities to poison the catalyst used and will lead to a significant decrease in the cell's performance. Problems with the hydrogen that is used is that it is currently an expensive product to buy, and it requires a larger fuel tank than that of gasoline. These factors, as well as the fact that it is not existing infrastructure for delivering hydrogen to consumers, are factors that are stopping these cells to be used in motor vehicles. This hydrogen is fed through a flow field that feeds the hydrogen to the anode. At the anode, the hydrogen is split into its protons and electrons. Platinum is the current catalyst used in PEM fuel cells, although alternative catalysts are being explored that are less expensive than platinum and are less poisoned by the impurities in hydrogen. The backing layer between the flow field of hydrogen and the anode is made of a porous carbon paper that is essentially the thickness of no more than 4 to 12 sheets of paper. This is used on the anode side of the fuel cell to help spread out the hydrogen gas so that as much of it reaches the surface of the catalyst as possible. The backing layer also serves the purpose to help the electrons conduct away from the anode and towards the external circuit to provide the energy of the fuel cell. The membrane of the PEM fuel cell is a polymer electrolyte membrane that resembles a thick plastic wrap and is essentially the thickness of 2 to 7 stacked pieces of paper. This membrane is used to allow the protons to flow through it and forces the electrons to flow to the external circuit. The polymer electrolyte membrane is also used to prevent the hydrogen and oxygen gases from passing through and combining with one another in any place other than the cathode. Once the protons have made it through the polymer electrolyte membrane and the electrons have made their circuit through the external circuit, both meet at the cathode, where the negative and positive charged ions combined with a flow field of oxygen to create water. The same catalyst of platinum is used in this process. Since this process is relatively slow, with current platinum catalysts, significant performance is lost. Researchers are looking for a catalyst that is less expensive than platinum and more effective. While there is a backing layer between the anode and the hydrogen flow field, there is also a backing layer of the same material between the cathode and the oxygen flow field. This backing layer on the cathode side prevents water vapor to reach the membrane, or allows water vapor to reach the membrane to humidify it, and forces the excess water to leave the cell to prevent a flooding of the cell. The backing layer also helps conduct the electrons from the external circuit to the cathode, as it is used also on the anode side to push the electrons to the external circuit. The whole process of this fuel cell creates the water that is allowed to collect at the cathode. Although the water can be cycled out of the fuel cell to prevent flooding, this process of creating water as a product is one of the current barriers to implementing them into motor vehicles. Water has a high freezing point and could cause many problems if implemented into motor vehicles when the weather gets cold. There are two types of PEM fuel cells that are used. One type operates at high temperatures, such as temperatures up to 200 degrees Celsius, and the other operates at temperatures of 80 to 100 degrees Celsius. Low temperature PEM fuel cells use water-based electrolytes, while high-temperature fuel cells use a mineral acid-based electrolyte. High-temperature fuel cells can tolerate CO impurities better than that of low-temperature PEM fuel cells. High-temperature fuel cells can handle impurities in hydrogen feed of up to 1 to 5% by volume, while low-temperature fuel cells can only handle impurities of up to 50 parts per million. Since the higher temperature fuel cells can tolerate the CO impurities better, hydrogen can be used from reformed natural gas instead of from purified hydrogen. Heat and water management can also be simplified, and reaction kinetics are faster at higher temperatures, potentially allowing for cheaper catalyst materials to be used. Operating at elevated temperatures is not solely beneficial, however, because the high temperatures result in a more degradation, including to, but not limited to, the corrosion of bipolar plates and catalyst support, along with the degradation of seals and membranes. As a result, durability of high-temperature PEM fuel cells is still a primary focus of all companies involved with the technology. Due to the positive and negatives, high-temperature fuel cells are not superior to low-temperature PEM fuel cells. Both technologies find a niche in where their benefits are preferable. To recap, Brennan discussed with you how fuel cells generally work and ongoing research for solid polymer electrolytes. Megan then went in to discuss the different types of fuel cells used in industry and the advantages and disadvantages of each. Finally, I talked about how exactly a PEM fuel cell works, along with the benefits of both low-temperature PEM fuel cells and high-temperature PEM fuel cells. The applications of polymers for fuel cells are very intriguing, and it will be interesting to see where the polymer research will lead future fuel cells in the future.